I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we'll solve one problem using Naïve Bayes algorithm. The case study is the weather prediction analysis. We'll see the problem. This is the problem statement. So this the same problem we have seen it in the previous lecture. Weather forecasting is a critical task in agriculture, disaster management, and daily planning. Meteorologists rely on historical weather data to make predictions about future conditions. Suppose a weather station wants to automate the prediction of whether it will rain on a particular day based on the previous pattern of weather features such as humidity, temperature, wind speed, and cloud cover. This we have seen it in the last lecture. In this case, in this lecture, what is the question is, so this is the table given, data set given. We have to find out what evaluation metrics would you use to assess the performance of your model, justify your choices, and what are all the limitations of Naïve Bayes in weather forecasting, and how the model be improved. Before going into the question, all we should know what is evaluation metrics and what is the necessary of evaluating the performances matrices. To evaluate the performance of a predictive model, especially in classification tasks such as weather forecasting, metrics like accuracy, precision, recall, F1 score, and the confusion matrix are commonly used. Accuracy provides an overall measure of correct predictions, while the precision focuses on the proportion of relevant positive predictions, and the recall indicates how well the model identifies all actual positive instances. The F1 score offers a balanced evaluation by combining precision and recall, making it particularly valuable when dealing with the imbalanced data sets. It is important for one to understand these evaluation metrics because relying solely on accuracy can be misleading. Different metrics reveal different aspects of model performance and help in making more informed decisions about model reliability and effectiveness. Here we have 10 rows are given. The four main parameters are humidity, temperature, wind, and sky, and the class label is rain, whether it will be raining or not. For this problem, we have to find out the evaluation metrics and what are all the limitations of the Naïve Bayes and how we are going to overcome this limitation. That will see. And first, in order to find out the calculations, performance measures, we need to find out we have to use the concepts of Laplace smoothing basics. The formula for that is for the conditional probability, we have to use it. Probability of feature value given class equal to count in class plus 1 divided by total in class plus number of possible values of the feature. And what is the real world analogy for this is a small survey might show zero preference for pineapple as a food. You should know why we are adding this plus one. For that, I am giving this explanation. This does not imply global dislike, only that it was not observed in the sample. And Laplacian smoothing accounts for such unseen possibilities. And the purpose of adding plus one, this plus one, we are calling it as Laplace smoothing. It prevents any conditional probability from becoming zero. Even all the values are here zero, it will be giving us 1 divided by some value. As zero probability causes the entire product in Naïve Bayes to become zero. This will become zero, which can mislead a classification. And adding this plus one ensures that each category has a non-zero likelihood, even if not observed in the training data. This is what we are adding here, plus one. This plus one, we are calling it as Laplace smoothing. And the concept of add plus one is it ensures the unseen feature values still contribute to the probability calculations and avoid zero. It avoids the zero. It prevents the entire probability from collapsing to zero, and it will improve the robustness. It makes the model more reliable on limited sparse data sets. And here, how we are going to in the from the Laplacian smoothing to conditional probabilities. In our problem, there are four values or variables are given. Humidity here, humidity, temperature, wind, and the sky. From this, we need to find out humidity has two values. What are all the two values? So it has two values: high, normal, and temperature if you are taking hot, mild, cool, and wind if you are taking strong and weak. Two values. Sky if you are taking clear, cloudy, and overcast. This is what we are. So humidity has two values: high, normal. Temperature has three values: hot, mild, cool. Wind has two values: strong, weak. Sky has three values: clear, cloudy, overcast. This we are writing it from the table. And for first row details, we have to consider first row details. This is the first row: hot, high, hot, strong, clear. And what is the prediction is yes. So we need to find out the value. The features are humidity high, temperature hot, wind strong, sky is clear. So this from the table we are writing high, hot, strong, clear, and prediction is yes, and actual label is yes. And we have to find out prediction of yes given feature is equal to prediction, the probability of yes given feature is equal to probability of yes into probability of high given yes, probability of hot given yes, strong given yes, and clear given yes. Similarly for yes, if you are finding out, automatically you should find out the probability of no given feature for all values. Instead of yes, we have to put a substitute no. And the first step is how many rows are there in this problem? There are 10 rows in this problem. So from this, yes, how many s's are there? This we have seen it in the previous problem. 1, 2, 3, 4, 5s and 5 no's are there. So the probability of s is given by 5 divided by 10 is equal to 0.5. Probability of no is equal to 5 divided by 10 is equal to 0.5. And we are approaching the, if we are applying the Laplacian smoothing, the probabilities, we use the that is Laplacian smoothing. Probability of feature is equal to x given class. What is the formula? Count plus 1 divided by total for class and the number of feature values. Let us humidity. How many values are there? Two values. And temperature, three values. Wind, strong and weak. Sky, we have seen clear, cloudy, and overcast. How many values are there? Three values are there. So the for class yes, total class is 5. The probability of 5 given s is equal to, we are finding out 4 plus 1. 4 plus count is 4. So in the from the first table, high is, how many highs are there? 1, 2, 3, 4 high, and 4 plus 1. The count is 4 plus 1 for yes alone. So you should not be confusing. You can be asking 5 highs are there. 1, 2, 3, 4, 5. And how many s's are there according the straight away to high? 1, 2, 3, and another high is yes. 4. 1, 2, 3, 4, 4 high values are there. So we have to find out count as for yes, total 5 high values count is 4 plus 1. This is the Laplacian smoothing. Total for class is 5, and the number of feature values how many? High and normal. 5 plus 2. So 5 divided by 7. We have to find out the value. And hot given yes. Hot, how many values are there? For yes alone, two values are there. Plus 1 Laplacian smoothing, and 5 s's are there. And here how many values are there? Hot, mild, and cool. Three values are there. So we are getting 3 divided by 8. Strong given s is equal to 2 strongs are given, or for is there for s. 2 plus 1 divided by 5 s is plus how many values are there for strong? 2. So there are two values are there for wind. Here we have to write it as a um, and 3 divided by 7. Similarly, probability of clear, how many values are there? 2 plus 1. From the table, we have to find out clear how many? 1, 2, 3, 4. And how many S's are there? 1, 2, the clear, 1, and here 2. So in that value only alone we are substituting. So 2 plus 1 divided by 5 plus how many the feature values are there? Clear, cloudy, overcast. So three values. We have similarly for no classes, total 5. Probability of high no. in this case, all values are, all high values are, there is no for high. Yes, yes, and here high, yes, and yes. There's no value for high. So we are writing it as 0 plus 1. This is the Laplacian value smoothing divided by 5 plus 2. How many values? High and normal. 1 by 7. Heart, no. How many hearts are there for no? We have to find out heart. 1, 2, 3, 4 hearts are there. How many no's are there? This is 1 and this is 1. So 2 values are there. So 2 plus 1, 3 values are there for heart. Yes, 1, 2, 3, and this we are writing it as 3 plus 1 divided by 5 plus 3 is equal to 4 by 8. Similarly, strong given no, 3 plus 1 divided by 5 plus 2, 4 by 7. Clear given no. Clear given no values given 3 plus 1 divided by 5 plus 3, 4 by 8. So step 3 is the compute the probabilities. For yes, probability of yes given all the values we have to multiply according to this formula. This we know that 0.5, all the values we found out, if you are multiplying, you are getting 0.0258. For no, if you are multiplying 0.0102. And here we have to compare. Probability of yes is greater than probability of no. So probability of S is greater than probability of no. What is the prediction? If it is greater than the S values, no, yes. Prediction is yes. So in the table, what is the value for corresponding first row? Yes. So this we are calling it as the true positive value. Since the actual label is yes, actual is yes, and the prediction is also yes. Hence, we are calling this as the true positive. Prediction is yes, given actual label is yes. So this feature we are calling it as the true positive. And row 2, humidity, temperature, wind weak, sky cloudy, and actual classes no. And prior probabilities, as like in the previous step we found out. And here S class count is 5, no class count is 5, humidity 2 values, temperature 3, wind value same thing. We have to find out for the second column. Second column we are, if you are second row, if you are finding out, we are getting the values like this. And then we have to compute the probabilities. If you are finding out 0. This probability of S given feature is 0.0152. This is 0.0214. So here no is greater than yes. What is the predicted value for the second row in this from this table? It is no. So no, it is matches with the predicted value. So this we are calling it as, see here for the second row we are getting no. So actual is no and predicted is no. This we are calling it as the true negative. This is negative, this is also negative. So we are calling it as true negative. Similarly, the features for row 3 is humidity high, temperature cool, wind strong, sky overcast. And actual classes, yes, if you are looking into, this is what we have seen previously. And S class, Y class, no class. And the unique values are humidity 2 values, the same thing. And if you are finding out for yes, we are getting the value like this, and for no, we are getting the value like this. Compute the probabilities. We have to add a 0.5 into all those values. So finally, we are getting 0.0096. And for this 0.5 into 2 by 7 into 3 by 8 into 5 by 7 into 3 by 8. If you are multiplying by and dividing, we are getting 0.0142. So this value is greater than this. How we are predicting? Probability of no is greater than probability of yes. Is equal to predict is equal to no. So the actual is yes, predictor is no. So this is the false negative, we can call it as. And similarly for row 4, actual value is this. So all those values we are calling it as, if it is matching, we are calling it as true negative, otherwise we are calling it as the true positive. And the conditional probabilities for another row, and here so this value, so 0.091, and here see here the value for no 0.0019. So in this case, yes is greater than no, yes, and predict is also yes. So this we can call it as a true positive. For row 6, similarly, we are calculating. If you understand the row 1 clearly, you can able to find out all the row values are very easily. So we have found out And here the probability of yes 0.0058, this is 0.0319. So probability of no is greater than probability of yes, the prediction is no, so this we can call it as the true negative. And similarly for row 7, and here the yes value is 0.0289 and this is 0.0079, yes is greater than no, so the predicted is yes and it is the true positive value. Similarly for 8, 0.0068 we are getting, and here for no probability 0.0255, so we are getting the value probability of no is greater than probability of yes, the value is no, and the table also it has been given it as no, this value we are calling it as the true negative. You parallelly compare the original data set. Similarly for row 9 we got probability of s is equal to 0.0255 and the probability of no is 0.0068, probability of yes is greater than probability of yes is 0.0255 is greater than 0.0068, so predicted is yes and actual is yes, predicted is yes, this we are getting it as a true positive. Similarly for row 10 we have to find out, and the probability of yes value was been given by got it by 0.0038 for no, and here some value we got it, so this value is probability of no is greater than that the previous value. So we are getting predicted actual is no, predicted is no, so the value is true negative. So after finding out we have to add another one more column over here, this is the full prediction. Actual value is what? Yes no, yes no, yes no, yes no, yes no, and predictor is also, for that the formula, you should know the formula, and after finding out we are applying with the formula we are getting predicted as also yes no, yes no. So if it is mean yes means two values are equal, we can call it as true positive, two values are no means true negative. False positive means here yes, here no means here we can write, we have to write it as a false positive, and here no, here yes, if we are getting we have to write it as false negative. Fortunately we are getting for all the values actual values are equal to, for all 10 rows all the actual values are equal to predicted value. So from this we have to find out the confusion matrix. So summary: true positive 5, true negative 5, false positive 0, false negative is 0. So all predictions are correct, that is perfect accuracy in this case. So confusion matrix, if you are taking predicted yes, predicted no, we have to write actual yes, actual no. So if these two values here we are getting it as true positive, suppose if you are getting the value here we have to write it as the false positive. Actual no, this is false positive, actual no, it is false positive, and here it is true negative, this value is 0.5. So from this we have to find out the performances calculation. Accuracy means what? It measures how many predictions were correct overall. As far as this case is, everyone is correct, all the values are correct. Accuracy, the formula is true positive plus true negative divided by all the values we have to sum up, true positive plus true negative plus false positive plus false negative. This confusion matrix, the researchers, you should understand very well about this confusion matrix, how you are arriving from the big data set. So finally this is the confusion matrix, we have to get it. From this only you are going to measure the calculation. So the accuracy is a true positive is 5, true negative is 5, 5 plus 5 plus 0 0, so 10 divided by 10 1.0, and the percentage if you are calculating 100 percentage. And the precision for S class, so precision tells us how many of the predicted yes rain were actually correct. That is given by the formula true positive divided by true positive plus false positive, 5 divided by 5 plus 0 is equal to 1 plus 100 percentage. Next, recall. Recall tells us how many of the actual yes were correctly predicted. This is given by true positive divided by here true positive divided by true positive plus false positive. Here recall is given by true positive, true positive. Here we have to substitute fn, false negative. Recall is equal to 5 divided by 5 plus 0, 5 divided by 5, 1.0, 100 percentage. And F1 score, this is very, very important performance metrics for the researchers, you should understand. F1 score is the harmonic mean of the precision and recall. It is useful when we want a balance between them. The formula is given by F1 score is 2 into precision into recall divided by precision plus recall. And the calculation is given by 2 into precision. We found out 1, recall 1, and precision plus recall 1 plus 1. 2 into 1 by 2. 2 will be getting cancelled. And the F1 score is also for this case, this case 100 percentage. And the final summary, if you are looking into, accuracy is 100, precision is 100, recall is 100, F1, but all the problem you will not be getting the value like this. The researchers, you should understand very well about this matrix. So from this data, we are coming into the conclusion that the model, the Naïve Bayes model, gave perfect predictions on this small data set. Hope everyone understood. Next, this some we have, even though we have got lot of advantages, some limitations also we have to go through. The limitations are, the first one is strong independent assumption. That means Naïve Bayes operates under the assumption that all features such as humidity, temperature, wind, etc., are conditionally independent given the class label. This means it believes that each feature contributes independently to the probability of the clash without being influenced by any other feature. However, in real world weather forecasting, this assumption rarely holds true. Weather variable are often interdependent. For instance, an overcast sky frequency accompanies high humidity. Both many indicates an increased chance of rain. Ignoring such relationship can lead to oversimplified model that misrepresent the true structure of the data, reducing predictive accuracy. Next, zero frequency problem. That means a key challenge in Naïve Bayes is the zero frequency problem, where if you have a specific feature values or class combinations never appears in the training data set, the model assigns it a probability of 0. For example, if no training data shows sunny with a high humidity and rain, then the model will assume that combination is impossible and discard it entirely when making predictions, even if it highly plausible in reality. This problem can be mitigated using techniques like Laplace. For that only we have used Laplacian smoothing, add one. Smoothing, which adjusts zero counts to small non-zero values. However, even with the smoothing, the core issue remains rare or unseen, even or still poorly modeled, especially in small data sets. And it continues feature handling. Whether data sets often include continuous numerical attributes like temperature, degree centigrade, wind speed, or atmospheric pressure. Naïve Bayes model don't handle these continuous variables natively. They require either discretization, example, converting temperature ranges into binary like cold, moderate, or hot, or switching to a Gaussian Naïve Bayes variant, which assumes that each continuous feature follows a normal distribution within each class. While Gaussian Naïve Bayes helps in continuous data, it introduces its own limitations. The assumptions of normality may not hold for many real world weather patterns. Discretization, on the other hand, can result in a loss of information or oversimplification of nonsense relationships. Next is sensitive to irrelevant features. Naïve Bayes does not have a built-in mechanism to ignore irrelevant or non-informative features. If your data set includes unnecessary variables such as day of week in weather prediction, they still get factored into probability calculations. Although such features may have no actual relations with the target variables, example rain, they can distort probability estimates and mislead to the model, especially if the irrelevant features have skewed distributions. This sensitivity makes feature selection a critical pre-processing step when using Naïve Bayes for weather forecasting or any other task. And limited expressiveness. Naïve Bayes models are inherently limited in how they capture feature interactions. They evaluate each feature contribution to the final prediction independently. This means the model cannot express complex conditions rules like it usually rains when it's both hot and humid, because it treats hot and humidity as separate, unrelated in future influences or on rainfall. So it lacks the representational power to model such conjunctions or joint dependencies, which can be critical in fields like meteorology, where weather phenomena often arise from interactions between multiple variables. As a result, naive Bayes may underperform when the target outcome depends on combined conditions rather than individual features alone. So, these are all the limitations and how we are going to overcome this prediction, the limitations. In order to overcome the previous limitations, you have to go for some other techniques. Use feature engineering. Feature engineering involves creating new features from existing data to better relationship between variable. For example, combining humidity and temperature into a single derived feature like that, we can call it as heat index. This we can call it as integration or hybridization. Anything we can call it as can help the model understand how these two factors together influence weather outcomes such as rainfalls or heat warnings. This approach enhances the model's ability to identify interactions that naive Bayes alone cannot naturally capture due to its independent assumptions. Next, apply Gaussian naive Bayes. Instead of converting continuous values like temperature or wind speed into discrete bins, Gaussian naive Bayes can be applied to handle them as continuous variables. It assumes that these features follow a normal, that is Gaussian distribution within each class. This allows this allows the model to use actual numerical values more effectively without losing information through discretization and making it more suitable for real world weather data. And hybrid with other models. Naive Bayes can be combined with other machine learning models to improve its predictive power. For instance, it can be used as base learner in ensemble methods like boosting or stacked with models such as decision trees. This hybrid approach helps overcome the limitations of naive Bayes by allowing more complex relationships to the modeled while still benefiting from naive Bayes simplicity and speed. Use conditional independence, that is Bayesian networks. Instead of assuming that all features are completely independent, a Bayesian network allows for modeling partial dependencies between attributes. For example, it can represent that sky condition is influenced by humidity, which is more realistic in weather systems. This makes the model more flexible and expressive, capturing real world relationships better than the naive assumptions of full independence. Next, cross validation for reliability. To ensure that the model performs reliability and is not just fitting to a specific set of training data, cross validation is used. This all researchers should know. This technique involves splitting the dataset into multiple parts, training the model on some parts, and testing it on others, and representing the process several times. It provides a more accurate estimate of the model's performance and help detect issue like overfitting. This and all we have seen it in the previous lectures, especially when working with the small data sets common in weather predictions. Hope this detailed discussion everyone understood very clearly. If you are applying it for your research, you can be able to get a very good result. Hope everyone understood this concept. The remaining things we'll discuss in the next lecture. Thank you.